Hey friends, welcome to McMills tutorial section, Econ 44 for econometrics. And today what we are going to do is just a tutorial session. Before I start, I would like to admonish each and everyone to subscribe to this YouTube channel, like and share so that anytime we post a video of this sort, you have easy access to it. I hope you find this tutorial useful. So friends, let's set the ball rolling. So this is our first question. We are being asked to consider a model, and we all know that this given model here is a multiple linear regression model. So given a regression model of this form, the emphasis we are laying here is that the x's are orthogonal. So therefore we are supposed to show that the b's, that's the estimates of b, that's b caps, from the multiple regression are identical to the coefficient estimate obtained by a simple regression of y on the corresponding x. Okay, now but then let me start by explaining what orthogonality means. So when we say orthogonality, for the statistical definition, orthogonality means that the regressors are uncorrelated. That's the independent variable. So what when I say the independent variable, what I mean here is x1t and x2t. I mean they are uncorrelated, meaning they don't have any relation. Okay, that's the if they are uncorrelated, then it that the covariance between them is going to be what? 0. So that's what orthogonality means. So now let's set the ball rolling. So what are we supposed to do? We have to show that the b's or the estimate of the b's from multiple regressions are identical to the coefficient estimate obtained by a simple regression of y on x. So we're looking at the case where the x's are orthogonal. Okay, we want to get the estimate. That's the estimate for the coefficient of regression, that's beta 1 and beta 2. We want it to look like when we had yt to be dependent variable and we have the x1 and x2 here to be the independent variable. Okay. So we are looking at the case where there is orthogonality. We are comparing it to our normal multiple linear regression. We want to get something identical. Okay, let's work through the solution. That probably you have to get what I'm trying to say. So this is the model that they gave us from our question. Okay, so now from last semester we can recall this. That from the multiple linear regression, we will have this regression model written in this form. This is the same thing here. Okay, so you can rewrite this one as yt to be equal to s beta plus mu. This is called the matrix representation of the multiple linear regression model. So this is the matrix representation. And this x here is what we have here, our x prime x. So if I want to estimate my y cap here, my yt cap here, to just give me a yt cap to be equal to s b cap. That's from this. Okay. So now I want to estimate for my x. So I want to get the matrices. So my x prime x, this is my x prime y, this is my beta cap, these are my beta caps, and this is my x prime y. Okay, this one we did last semester, so I hope you all can recall. So if I want to get my beta cap or my b cap, this is the formula. So now from the question, what we are trying to do is that even though they've given us the condition that the x's are uncorrelated, okay, but we want to get an answer, the estimate for the regressors, that's why the regression coefficient to be identical. So it should look like this. Like we want something similar like this. Okay, if they are identical, it means they have something in common. Okay, so we want it to look like this one. Okay, so now let's work. So given that the x's are orthogonal, okay, so from this is the model that they give us. So if they are orthogonal, then it means that they are uncorrelated. So it means x1 can stand alone and x2 can stand alone. So our x prime x matrix will be in this form. Because of the orthogonality, it wouldn't look like this. It will look like this. So this will be our x prime x matrix. Okay, so because of the orthogonality, you have x prime, s1 prime, x1, and that's for the first row, that's row 1. and we have S1 prime S2. For row 2, we have S2 prime S1, we have S2 prime S2. And these are estimates because these are the regression coefficients. That's beta 1 and beta 2. Those are the ones which has what regresses. So these are parameters, and these are x prime y. So we have x1 prime y and we have x2 prime y because of the orthogonality. They stand alone. Good. So if the x's are orthogonal, then it implies that, as I said earlier, orthogonality means they don't have any relation. So then it means that x1 prime x2 will be equal to x2 prime x1, and both of them will map to 0 because of they don't have any relationship. So it means that because of the orthogonality, from the normal equation, this is what we are going to get. So like this is what we are going to get. So if you want to estimate for beta 1 cap, we end up getting x1 prime s1 inverse. Sorry, here is supposed to be s1. So my beta 1 cap will be s1 prime s1 or inverse s1 prime y. Okay, also looking at this, because of the orthogonality, my beta 2 cap will end up getting x2 prime x2 or inverse x2 prime y. So this is all because of the orthogonality. They don't have any relation. So this s1, s2, and s2, s1 here, they all map to 0. So this, and when we compare this to that, okay, we can see that we've gotten something identical. You can see that we have something identical. It looks like this. So that's what the first question is trying to tell us to do here. Now let's go to the B. The B says that we should also show that the total sum of squared residual is just the sum of the sum of squared residual of all simple regressions. So these are regressors. Okay, these are regressors. So what this question is trying to show is that when I find the residual sum of squares, okay, the total residual sum of squares for x1t and x2t, I should end up getting it to be equal to the sum of squared residual for all the regressors. That's x1t and x2t. So now let's walk through a solution. So in the nutshell, this is what the question is trying to tell us to do. So in the nutshell, we want to get this. Okay, we are being asked to show that the total sum of squared residual. So this is the total sum of squared residual. That's SSR for x1 and x2. Okay, should be equal to the sum of squared residuals for all the regressions. So we want to get the total sum of squared, that's SSR, to be equal to the sum of squared for all the residuals. So we should get the total sum of squared residual for S1 and S2 to be this form. So this is our end result. I always used to say that I have this thing I always say that we have to know the end result and we play around it. Okay. So we want to end up getting, so this is what the question wants us to prove. So this is our end result. So let's play around the solution. So for last semester, let's recall. So if we want to get the total sum of squares, so the total sum of squares here will be the sum of squares residual plus the sum of squares explained, or the explained sum of squares. Okay, great. So this is our equation 1. Because the regressors we have here, because of these regressors, we just have x1t and x2. We have only 2 regressors. So our total sum of squares, right? So our total sum of squares here will be equal to sum of squares residual x of x1, x2 plus explain sum of squares of x1 and x2. So this will be our equation 1. Okay. So now if I want to, so I want my, so what I'm looking out for is sum of squares residual for s1 and s2. Okay, so I want to eliminate this. I want to rewrite this where I'll only get SSR in it. Okay, so I want to rewrite this in a form where I'll only have it in terms of SSR. So if I want to estimate for SSC, this is how we estimate for SSC. SSC for S1, S2 is equal to SSC X2 minus SSR x1 giving x2. Okay, someone can also do SSE of x1 x2 to be equal to SSE of x1 minus SSR of x2 giving x1. When we do it different ways, we all end up getting the same answer. So now I have SSE of S2 here. I have to eliminate the SSE of S2 where I'll only get it in terms of SSR of S2. So the SSE of S2, this is the formula. I'll end up getting trimestic for SSE of S2 to be equal to SST minus SSR of X2. This is my equation 2. Okay, so now I've gotten my equations ready. Let's try and do some substitutions and we end up proving it. So now, from equation 1, I want to find SSR for all the regressions. So this is what the question is trying to tell us to show. So my SSR, making SSR the subject here, SSR for S1, S2, I end up getting SST minus SSC for X1, X2. Okay, so now when I substitute equation 2 into equation 4, when I do the change of subjects here, this will be my equation 4. So when I substitute this equation 2 into equation 4, this is my equation 4. This means that wherever I see SSE in equation 4, I will substitute everything here. SSE of S1, S2. So here in equation 4, I have SSE of S1, S2. So when I substitute, this is what I get here. So after my substitution, I do what? Expand. So when I expand, this is what I get. And now this, I name this my equation as equation 5. And you see I have SSE of X2 and equation 3 to I have equation 3 is SSE of X2. So I'll do another substitution where I substitute equation 3 into equation 5. Equation 3 to equation 5. So when I do my substitution, wherever I see SSE of X2 in equation 5, I substitute equation 3 in it. So when I do my substitution, this is what I get. After expansion, you can see that my SST here will cancel this SST. So I'll end up getting my SSR X1, X2 to be equal to SSR of X2 plus SSR X1 giving X2. Okay, so you can see that the total sum of squares residual only has the sum of squared residuals of all the regression. So the total sum of squares residual for X1, X2 is equal to SSR X2 plus SSR X1 giving X2. So that's what the question 4B is trying to tell us to show. Okay. So I hope you find this tutorial useful. So let's go to the next question. So the next question says that if sigma squared ui is equal to k squared f of x, where k is a constant, what is the consequences of on the OLS estimate? Okay, so now one thing we should know is that, but let's work through the solution. I would like to show you something here. Now, from the question, okay, from the question above, from this question, we can see that we have the presence of heteroscedastic. The regression coefficient here is heteroscedastic because of the variance of the error term here will vary. Okay, it varies. It's not constant. We know that for the estimate or the OLS estimate to be homoscedastic, then it means that the variance of the error term is what constant. Okay. Then heteroscedasticity also doesn't improve the precision level, so it doesn't give an accurate precision about the regression estimates. Okay, because so here, what is the consequence on the OLS estimate? The consequence is that it makes the regression coefficient or the OLS estimate heteroscedastic, and hence it affects the precision level. Okay, so now let's go to the B. We are being asked to show that or show how heteroscedasticity is eliminated if we apply OLS transformation to this model. Okay, so now let's walk through the solution. So from A above, this is what was given, and this whole expression is the variance of ui. Okay, and you can see the variance of ui here is not constant, so it's heteroscedastic. And from this equation, we end up getting this as a regression model. So this will be our regression model. So it will be in the form y to be equal to beta naught or b naught plus b1 fx plus ui. Okay. So if I want to correct the heteroscedasticity, I would have to divide through by square root of fx. Okay. So when I divide through by square root of fx, so this is what I've had here. Okay. So I just represented y on root of fx to be equal to y star, beta naught on root of fx to be equal to beta naught star, and beta 1 fx on root of fx to be equal to beta 1 fx star plus u on root of fx to be equal to, I just represented it to be equal to u star. Okay, so I've just changed the form or the format of my regression so that I will end up getting a new regression model to look like this. Okay, but we should have in mind that u star here is this, beta b naught is this, b1 fx here is now this, and our u star is this. That's what you have to have in mind. So if you want to prove for homoscedasticity or heteroscedasticity, we try and find the variance of the error term. And now this is our new error, u star. I'll find the variance of u star. When I find the variance of u star, I'll end up getting v, denoting the variance, representing variance, v of u on. So this is my error. So v of u star will be equal to v times u on root of fx. Okay. So now when I find the variance, you see this, the variance of everything here will be 1 over fx, because to be 1 squared on square root on fx all squared, and the squared will do away with the square root here. So I'll end up getting this times the variance of u here. Okay. Knowing that the variance of u from equation 1, variance of u here is k squared f of x. So when I substitute my variance of u here, my f of x here will cancel this f of x here. So my variance of u star will just be equal to k squared. And since the variance of u star here is equal to constant, and you know that for homoscedasticity, the variance of the error term is always constant. So hence, have been able to resolve the problem of heteroscedasticity. So now, this all that this tutorial session was trying to show. So I hope you all find this tutorial session useful. Thank you. Let's not forget to subscribe to this YouTube channel so that anytime we post a video of this sort, you'll be able to have easy and quick access to it.